single railroad rail, nearly 400 feet long, can weigh more than 15,000 pounds. It is a steel beam engineered to carry hundreds of tons and endure decades of service. But how is iron transformed into a rail this long? And how are these rails turned into track for the world's fastest trains? To find out, we visit a leading producer of extra-long rails, then follow a track-laying factory on wheels. High-speed trains can travel at more than 215 miles per hour, close to the top speed of a Formula One car. But an F1 car weighs less than a ton, while a train may weigh hundreds. At those speeds, tiny irregularities become serious forces. Traditional tracks used shorter rails joined with bolted plates. Every time a wheel crossed a joint, it created an impact and the familiar click-clack sound. At 190 miles per hour, repeated impacts would increase noise and stress on the track. High-speed lines therefore use long rails welded continuously, with smooth curves and precise geometry. The story begins in Donawitz, Austria, surrounded by the mountains of the Austrian Alps. Here, voestalpine produces unwelded rails up to 394 feet long. Production begins with iron ore, coke, and limestone inside a blast furnace. Hot air makes the coke burn hot enough to reduce the ore and melt the iron. Liquid iron collects below lighter slag, and both are drained separately. The molten iron is then refined into steel. Oxygen removes excess carbon and unwanted elements, while carefully measured quantities of carbon, manganese, silicon, and other alloying elements are added to create the exact steel grade required for the rail. The chemistry is tightly controlled. Rail steel must resist wear while remaining tough enough to bend and absorb impacts without cracking. The liquid steel is transferred in a large ladle and fed into a continuous casting machine. A ceramic tube shields the flowing metal from air that could contaminate it. Inside a water-cooled mold, it solidifies into a rectangular section called a bloom. Once the strand has solidified sufficiently, cutting torches divide it into blooms roughly 40 feet long. A crane transports them to a reheating furnace. There, the steel is heated evenly to around 2,200 degrees Fahrenheit, making it soft enough to be reshaped without melting. Glowing blooms emerge from the furnace. Before rolling begins, high-pressure water jets blast the surface. Heating creates a brittle layer of iron oxide known as scale. The water breaks this scale away, preventing it from being pressed into the finished rail. The cleaned bloom enters the rolling mill, where enormous steel rollers squeeze and reshape it repeatedly. It resembles an industrial pasta machine handling tons of red-hot steel. During each pass, the bloom becomes longer and its cross-section becomes smaller. Specially shaped rollers gradually create the rail's familiar profile: the wide foot at the bottom, the narrow web in the center, and the thick head on top. The head carries the wheels, the web transfers the load, and the foot spreads it across the railroad ties. By the time the steel leaves the final rolling stand, a bloom that began at about 40 feet may have become a rail up to 394 feet long. For heavy-duty track, the railhead may be heat-treated while still hot from rolling. In voestalpine's head hardening process, the head is cooled under carefully controlled conditions. This changes its microscopic structure and hardens the running surface deeply. The result is greater resistance to wear and rolling contact fatigue, especially on curves and heavily loaded routes. It does not eliminate friction, it helps the rail retain a smooth shape longer. After rolling and cooling, the rail is rarely perfectly straight. Uneven temperature changes can leave small vertical or horizontal curves. To correct them, the rail enters a roller straightening machine. One set of rollers bends it vertically, while another corrects it from side to side. The machine applies carefully calculated forces that move the steel slightly beyond its elastic range, removing unwanted curvature. Too little pressure and the rail springs back. Too much pressure could create harmful stress or distort its profile. Sensors continuously measure alignment, and the machine adjusts the rollers until the rail falls within strict tolerances. Next, the ends are trimmed to their final dimensions. The first and last portions passing through the rolling mill may not have exactly the same shape as the rest of the rail. Large water-cooled saws remove these ends and produce flat, square faces. This is important because the rails will later be welded together, and poorly cut ends would make an accurate joint more difficult. Before leaving the factory, every rail undergoes a detailed inspection. Cameras and laser systems measure its dimensions, straightness, surface condition, and complete profile. The acceptable variations may be only a few thousandths of an inch, because slight differences can affect wheel contact, vibration, and long-term wear. This is especially important on high-speed lines, where a tiny change in the rail profile can alter how the wheel meets the steel and gradually increase vibration, noise, heat, and maintenance requirements significantly over time. Additional systems search for defects that cannot be seen from outside. Magnetic testing can reveal certain cracks or surface irregularities by measuring disturbances in a magnetic field. Ultrasonic probes send high-frequency sound waves through the steel. Reflections from those waves can reveal internal inclusions, voids, or cracks hidden beneath the surface. If the equipment detects a suspicious signal, the rail is examined again. Any defect that exceeds the permitted standard can cause it to be rejected. The final factory challenge is moving a rail nearly 400 feet long. Magnetic lifting systems and specialized handling equipment raise several rails and place them across a train of connected railcars. The steel is supported at many points so it can flex safely as the train travels around curves. The rails are secured to prevent uncontrolled movement, but they are not treated like fragile glass. Small cosmetic marks are different from structural damage, and any serious damage is evaluated before installation. At the worksite, a track renewal train takes over. This enormous machine is effectively a moving assembly line. Depending on the system and working conditions, it can remove old track and install between 1,600 and 6,500 feet of new track during a day. Long rails arrive on specialized railcars. Hydraulic guides move them into position, while concrete railroad ties travel through the machine on conveyors. As the renewal train advances, it places the ties at precise intervals. Rollers then guide the rails onto fastening plates mounted on top of each tie. Fastening units secure elastic clips around the rail foot. These clips hold the rails firmly while allowing tiny controlled movements caused by load and temperature. Once the rails are attached, the track still needs support and precise alignment. A tamping machine lowers vibrating metal tools into the ballast, the crushed stones surrounding the ties. The tools squeeze and compact the stones beneath each tie, while the machine lifts and aligns the track. This gives the track the correct height, level, and curve. On bends, the outside rail may be raised above the inside rail so trains can pass through more smoothly. The separate 394-foot rails must now become a continuous line. One method used to join them is aluminothermic or thermite welding. Workers align two rail ends with a carefully measured gap between them. A refractory mold is clamped around the joint and the rail ends are preheated. Above the mold sits a crucible containing iron oxide and aluminum powder. When the mixture is ignited, aluminum removes oxygen from the iron oxide in an extremely hot chemical reaction. The reaction produces molten steel and aluminum oxide slag. The molten steel flows into the mold, fills the gap, and fuses with the heated rail ends. After the joint solidifies, the mold is removed. Excess metal is sheared away, and grinding machines restore the exact shape of the railhead. When finished correctly, the wheels pass across the weld without striking a step or gap. Through repeated welding, individual rails become continuous welded rail stretching for miles. The result is quieter, smoother, and better suited to high-speed service than old-fashioned bolted joints. That is how iron becomes one of the most precise and heavily tested components in modern transportation. And that is how giant rails are manufactured, inspected, transported, installed, aligned, and welded into the tracks beneath some of the fastest trains on Earth. If you enjoyed the video, leave a like, share it with someone who might find it interesting, and subscribe with notifications turned on to keep discovering how the modern world is made.